Run the exact same code on a tuned server cluster, and then execute it on a struggling, decade-old laptop. You'll get completely different execution times. This makes measuring software speed in seconds a flawed metric. Physical time is hopelessly entangled with compiler optimization variances. Unpredictable system loads and silent background processes pollute absolute time measurements, altering the stopwatch results from 1 millisecond to the next. To evaluate the inherent efficiency of the code itself, we have to completely decouple our analysis from the physical hardware executing it. This graph plots resource consumption. Instead of tracking localized speed, we ask a strictly mathematical question. What happens to the required resources as the input size, n, grows arbitrarily large? At a massive scale, execution paths diverge radically. The best, average, and worst-case scenarios for a single algorithm take entirely different trajectories. We define this hardware-agnostic evaluation method formally as asymptotic analysis. An algorithm's true engineering worth is defined by its mathematical category, not its stopwatch speed. We measure it by proving its ultimate limit of growth. To calculate these limits, computer scientist John von Neumann realized we needed an idealized universal computing architecture. He devised the random access machine, or RAM model abstraction. It operates on one strict rule. Every single simple operation takes exactly one discrete step. We can apply that rule directly to the code. Look at this C function calculating a partial sum. We begin with the static operations, initializing a variable and returning a value. Under the RAM model, each independent action takes exactly one execution step. The for loop is where complexity multiplies, because its execution is entirely dependent on the input size n. The initial counter assignment runs once. The Boolean condition checks n plus 1 times, executing until it fails. The counter increment runs exactly n times. Sum those discrete computational steps together, and we derive an exact execution polynomial representing the algorithm's total runtime. F of n equals 2n plus 3. But as our input size n approaches infinity, lower-order constants like the plus 3 lose all relevance to the final calculation. Even the constant multiplier of 2 drops away. It cannot dictate the overarching trajectory of the curve at an infinite scale. We track microscopic operations so we can deliberately strip them away. This deduction isolates the dominant term that governs the algorithm's absolute complexity. With the dominant term isolated, we must categorize this polynomial against known mathematical functions to establish its limits. This chart graphs our algorithm, f of n, bounded entirely below a secondary curve, c times g of n. This is big O notation. It provides a guaranteed upper bound, proof that the code will never scale worse than this specific ceiling. Crucially, the formula f of n is less than or equal to c times g of n only applies after the intersection point, n0. We only care about the performance as it pushes toward infinity. By reversing that logic and placing a bounding curve strictly beneath our function, we establish omega notation. This dictates the algorithm's absolute mathematical floor, or its best-case execution time. If we can bracket a function perfectly between an upper and a lower constant adjusted curve, we achieve theta notation. This is a tight bound, the exact mathematical reality of the algorithm's scaling factor. In the commercial software industry, engineers frequently use Big O as a blanket term to describe all complexity, entirely omitting the calculation of lower bounds. Stating an algorithm is merely bounded above is incomplete engineering. A rigorous profile requires defining the ceiling, the floor, and the tightly bound reality between. Modeling static linear loops is predictable, but complex sorting algorithms alter their execution paths based entirely on the shape of the data they ingest. This graphic displays the pseudocode for an insertion sort, aligning each line with its operational cost factor and iteration count. First, look at the best-case scenario, feeding the algorithm an array that is perfectly sorted in ascending order from the very start. With the values properly aligned, the inner while loop condition immediately fails on every pass. The subsequent swapping logic never fires. Stripping the inner loop out collapses the execution sum into a basic linear equation. In this specific configuration, the algorithm hits its omega n floor. Now invert the data. The array arrives sorted in complete reverse order. This maximum disorder forces the inner loop to evaluate and execute for every single element in the array, driving the operation count to its absolute peak. The cascading operations form a distinct algebraic summation series, 1 plus 2 plus 3, ascending steadily all the way to n. Resolving that series mathematically yields n times n plus 1 over 2. The massive dominant term exposed here is n squared, proving a definitive worst-case complexity of order n squared. The logic does not possess a single static speed limit. Its efficiency is a dynamic spectrum, governed entirely by the initial entropy of the data. Tracking CPU cycles only accounts for processing time. We also must calculate the physical footprint of memory allocation. Modern storage capacity is vast, but at an extreme algorithmic scale, allocated memory remains a strictly constrained resource. Inefficient allocation will break a system just as quickly as a slow processor. Space complexity analysis holds one distinct advantage over time complexity. While a processed CPU cycle is gone forever, memory addresses can be continuously overwritten and reused during execution. This chart profiles the greatest common divisor algorithm. It serves as a benchmark for extreme memory efficiency. Scanning the logic, we find the absolute limit of required allocation. It relies strictly on 3 integer variables, m, n, and a temporary placeholder t. It does not matter if the input integers are single digits or massive cryptographic primes. The system requires exactly 3 variables to execute. The allocation never scales. We classify this perfectly flat memory footprint as having order 1 or constant space complexity. In applied systems architecture, these two forces constantly collide. Engineers negotiate brutal trade-offs every day, burning heavy CPU time to save critical memory, or sacrificing RAM capacity to execute faster. Asymptotic bounds equip us with the rigorous mathematical foresight to plot these limitations. They allow us to predict and eliminate catastrophic system failures on a whiteboard long before a single line of code ever hits a production server.